It is like a finger pointing away to the moon. Don't concentrate on the finger or you will miss all that heavenly glory. Empty your mind, be formless, shapeless, like water. Like water. Water can flow or it can crash. Be water, my friend. Empty your mind, be formless, shapeless.
I gotta say, Josh, you have like the most eclectic taste in music ever. You find like all of these incredibly random things.
What was that one from?
That was actually from Miles.
Oh.
It's actually from, I got it from Ed Kmet, actually. I have no idea why he tweeted it, but he tweeted it one day. And I thought, wow, I have just got to use that as the theme tune for Shapeless.
I was going to say, you have a theme tune now. That is so awesome.
Yeah.
Miles' theme tune.
It's basically excerpts from an old interview with Bruce Lee. I'm not quite sure who he's being interviewed by, interspersed with cuts from a variety of Bruce Lee movies. It's great. The way to find it is just go to YouTube and search for "Be Like Water, My Friend," and you'll get it. It's the top hit.
Excellent.
As it should be.
We'll put a link in the show notes so everyone can follow along.
So just play it on loop while they're listening to us?
Yeah, we'll provide an alternative soundtrack to this. So
exactly,
instead of listening to us, you can just listen to the music over and over again.
The only reason people like tune into the podcast is to just watch us. Like, there's no value in the audio.
Oh dear.
No, I have actually used that as an intro to a Shapeless workshop.
Excellent.
Yeah, it went down pretty well.
So, are we going to introduce what we're doing here?
We should introduce what we're doing, who we are, and all that stuff. You want to kick us off, Dick Wall?
Sure. Okay.
Or should I say Bill Venners?
Which episode number is this?
This is episode 17.
17. Okay. So, welcome to episode 17 of the Scalawags, and we have a special studio guest. Well, I don't think you can really call it a studio if he's in actually another continent.
Distributed studio. Cloud studio.
A cloud, in our cloud studio, we're happy to present Miles Sabin. Oh, Miles, how do you say your last name?
It's Sabin.
Sabin. I've been saying it wrong all this time. And you never corrected
I worked with
me.
you for like 2 years, and I still thought it was Sabin.
I probably have corrected you, but you probably weren't paying attention.
Yeah, that sounds like me.
All right, so let's do our intros. I'm Dick Wall.
Pretend it's spelled with 2 B's, and you'll never get it wrong again.
Got it.
That's the one.
So I'm Dick Wall, Escalate Software, not Bill Venners.
I'm Bill Venners, Rich Relevance.
Seth Tissue, Boston enthusiast, Boston Scala enthusiast. I'm a Boston enthusiast today, actually. I spent the afternoon on my bicycle and biking around downtown Boston. It's beautiful.
Excellent. You think you have to say it Boston? I believe if you don't say it like that, they throw you out.
Maybe another decade.
Well, right now we're in the cloud studio, so he's safe. He's protected.
Yeah.
It's
Yeah, our cloud studio is safe from Heartbleed.
Yeah. So I'm Josh, right? I'm with TypeSafe. I'm a nerd in all fashion, and apparently a catcher of raccoons.
Yes, and then a flame broiler of raccoons as well, judging from the picture.
This was my morning.
Flame broiler of raccoons.
It looks like he's caught it.
Wrong with Pennsylvania?
It looks like he's caught it, and then like it's been charred to a nice crispy finish.
This is Richard Wall, the raccoon. He is now safe and secure in PA Gamelands 208 for anyone who wants to go visit him.
Oh. Hello, Doc.
Look, another raccoon. Oh.
More barbecue.
So this episode is going to be all about Shapeless, where we basically ask Miles to inform us of any misconception we may have. Which I think the first one is, Shapeless just H lists?
I was gonna do a slightly more slick one, but when I use Shapeless, when I reach for Shapeless, it's always for H lists.
Well,
I am aware that there is other stuff in there, but I would love Miles to go through the other stuff other than H lists that is.
So when I reach for Shapeless, it's for encoding every time. Like the codecs are so great.
Oh, okay.
maybe we should back up and like ask Miles who he is and what Shapeless is.
Good plan.
No.
I think I just did.
Okay, so my name is Miles Sabin. I am a type astronaut and dog walker. No, seriously, I'm a partner in Underscore Consulting, which is a Scala consultancy based in the UK, mainly in London, but I'm in Brighton. So I've been working on Shapeless amongst other things for I don't know, I guess it must be nearly 3 years now, maybe 4 even, possibly. I mean, since the very earliest beginnings of it. Well, I guess it started off as I think at one point I remember Paul Snively sort of in an unguarded moment he described it off the cuff as a vanity, as a show-off project, and I think at one point it actually was kind of something along those lines, but it's since developed into something which I think is hopefully a little bit more interesting now. But anyway, yeah, so I'm here to field all and any questions that anyone might have about Shapeless, what it is, what it's for, why, what on earth does it mean. What's this strange thing that's happening to the inside of my head when I try and look at the code? Anything along those lines, I'm here to answer those kind of questions.
So first off, is it true that Bruce Lee used Shapeless?
That's right. In the famous scene where he defeats
one of the bad guys. One of those bad guys that he fights. Yeah.
Yeah.
You know that bad guy. Yeah.
The really bad guy, the one with the little skinny moustache that turned up at the end. That was Shapeless.
Absolutely.
Yeah.
Yeah. You will be invincible. You will be completely invincible if you.
So, I guess so. You wrote it as kind of a show off project, possibly self-admitted. I don't want to put. It was kind of a showcase for. At the time, I was doing or trying to do. Scala training, specifically advanced Scala training, and the best way, I suppose, I thought at the time to kind of showcase that my chops at.
There's the dog.
Hang on, I'm going to have to take a short break.
We have two special guests today.
Apparently, there's a pretty serious fight going on out there or something. I wouldn't want to be that postman.
There's a raccoon in the yard.
Yeah, or a postman has just
Josh's
been
raccoon booked a flight.
Welcome to Scalawags.
Best episode ever already.
Yeah. So we're just gonna mute Miles for a little bit.
Yeah.
Mute him when he comes back.
We're gonna miss it when the screaming starts.
Yeah. It's like Hound of the Baskervilles over there.
Hey, while we've got a second, can I do a bit of shameless self-promotion?
Yeah, go for it.
Okay. We've only just sort of put this together, but we are having a Java Posse Roundup UK version in less than a month now in London, June the 10th and 11th. If you want to know more about it, go and check out the Skills Matter site. I think it should be really good. It's right before DevOps UK, so it came together really late, and I promised people I'd try and get the word out. So
awesome. Miles, I muted your microphone. I think you need to unmute it. Okay.
There we go.
Yeah, sorry about that, folks.
That's all right.
Unscheduled.
Your dog seems to be very keen on Shapeless. Does he use the H lists?
Well, no, he's actually he's moved on from the H list to other
okay.
So I feel like one thing we should start off with, since most of us, when we think of Shapeless, we think of H lists. Possibly we should actually describe what an H list is.
Sure. So an H list is it's a data structure which is, I suppose you could best think of it as being a hybrid of something which is on the one hand tuple-like. So a tuple is a thing which has multiple elements, but a fixed number of elements. But each of the elements of the tuple can be of a different type. So it's a hybrid of a tuple, and on the one hand, and on the other, a list. A list is again a multi-element data structure, but it has a variable, or at least as far as the data type is concerned, any individual value is going to have a fixed number of elements, but the data type itself has values which can have an arbitrary number of elements. However, all of the elements of a list must be of the same type. So an H list takes the variable length aspect of vanilla lists and the heterogeneous the idea of elements having different types of tuples and combines those in a single data structure. So you can think of them as being either lists which can support elements of different types, or a tuple which is variable length.
Yeah. So now, just to clarify on that, get into the questions. The variable length, as long as it doesn't violate the type that it is. So you specify the list type with the elements that will be in there, and then you specify the list itself, correct? But you can let the type inference do the second or the first part for you to actually provide.
Yeah. Typically, I mean, the types that you end up getting when you're working with these kinds of things tend to be somewhat large and complex, and typically things that you wouldn't necessarily want to write by hand. So by and large, in many ways, actually half of the trick in Shapeless is actually being getting the complex types that are at work in Shapeless as smoothly inferred as possible, given the constraints of Scarlett's type inference.
Right.
So by and large, you would not expect to actually have to write an explicit H-list type for anything. Typically, you would either be working with values where the H-list types are inferred, or possibly even just with type variables and bounds where the whole content of an H-list is inferred from some other set of values somewhere else in your in your program.
Cool.
Well, my understanding is that I haven't looked at the details of Shapeless's H-list in like 2 years, but when I've done H-lists in Scala in the past, the typing on them is actually not all that terrible. Like there's a lot of weird implicit machinery at play, but like writing the type of a H-list is actually very straightforward. So does Shapeless have to do something different in order to get all of the tricks that it gets out of an H-list, or is like H-list just like kind of the simplest example of some much more complicated stuff that?
Well, the simplest example of an H-list that you can sort of take the head and tail of, and that you can prepend an element to. You can write in half a dozen lines of code in Scala. It's really very, very simple. The thing about writing the types themselves being straightforward, I mean, that's absolutely true. I mean, an H-list type is essentially just a list of types with some separator and some kind of a terminator. That's not terribly difficult to write. On the other hand, how often do you want to have to explicitly write types? I mean, ideally, in all cases, H-lists or otherwise, you would prefer to have your types by and large inferred, unless they're part of a public signature of some sort or another. So yeah, you're absolutely right. H-list types aren't especially complicated. On the other hand, we don't particularly want to have to write types at all if we can avoid it, I think.
I think it's worth making sure it gets said early on. So H-list it's one of the first answers that Shapeless provides, but like, well, what question is it asking? And what question is it answering? And my observation on IRC is that when Shapeless gets offered to people is when they're trying to write code that works on all tuples, regardless of size, all functions, regardless of how many inputs they take, or something that operates on all case classes. and H-lists are something that are useful in all three of those situations.
Yeah, I think that's right. So I think maybe what I should do is sort of give a little bit of a history of Shapeless and how where it came from to start with, and how it's sort of ended up where it is now. So the first sort of outing that Shapeless had really didn't particularly involve H-lists at all. It started off with an implementation, really pretty much just a proof of concept implementation that I put together of something called Scrap Your Boilerplate in Scala. Scrap Your Boilerplate is an approach to something called generic programming in Haskell. The original sort of series of, I think, 2 or 3 Scrap Your Boilerplate papers were written by Simon Peyton-Jones and Ralph Lamel. Very interesting stuff. The variant of Scrap Your Boilerplate I ended up implementing was the one described in their paper, Scrap Your Boilerplate with Class, which is kind of a type class based encoding of generic programming in Haskell. I kind of looked at that and thought, well, you know, we know how to encode type classes in Scala. It looks like we ought to be able to do this kind of thing in Scala, and so I kind of set myself. Well, I kind of set myself up for this by volunteering to do a talk at a conference in London in advance of actually working out how I was going to do this stuff. And to make matters worse, it was a conference that Simon Peyton-Jones was keynoting, so he was going to be in the audience. So I really had to make sure I was going to get this thing right. Turned out it was doable. It was very interesting learning experience for me. I ended up exercising a whole bunch of exercising, learning, inventing in some cases a whole bunch of tricks and techniques that have turned out to be extremely useful and interesting. Just winding back a bit, I suppose I've kind of introduced this by sort of half assuming that people know what one Scrap Your Boilerplate is. And Scrap Your Boilerplate and generic programming. So Scrap Your Boilerplate is a particular library for doing generic programming in Haskell. It's since been, I think, probably fair to say, superseded. SPJ may hate me for saying this, but it's been. I think it's probably fair to say it's been superseded by other approaches to generic programming in Haskell since those papers were written. But generic programming itself is a best way to. So one of the best ways I've heard it described as. It was actually by one of the organisers of last year's workshop on generic programming at ICFP last year. As it's generic programming is the kind of polymorphism that your language doesn't support yet, which I think is kind of nice.
So this is an ever-evolving sort of self-referential definition, because doing generic programming in the language means by definition that your language must support it. So therefore, you're not actually doing generic programming.
That is absolutely right. But paradoxes aside, I mean, I think. Well, I mean, it's kinds of polymorphism that your language doesn't support in a first-class way yet.
Yeah,
okay, another way of describing
not natively.
That you have to be clever and possibly evil in order to do it.
Perhaps. All right. Another way of saying it is maybe it's second-class polymorphism. It's not first-class in the way that, say, type, a simple ordinary parametric polymorphism or subtype polymorphism are first-class in Scala, say. But it's something you have to do a little bit of work to encode it. By the way, can anyone actually hear the sounds of digging in the background?
Yeah.
Vaguely, but it's not bad.
Okay, that's cool. I think my actually not my dog, but a guest dog has decided he's found a bone somewhere theirs, and has decided he has to try and find it. So it's kind of polymorphism on steroids, and specifically it's about polymorphism which abstracts over the sort of a fairly abstract and general idea of shape that data types might have. we're kind of it's a sort of somewhat vague notion, the idea of a shape, but it's the kind of thing that you could imagine capturing by thinking in terms of say the number of elements of a tuple, or the depth of nesting of some nested hierarchy of data types or case classes, or something along those lines, or it's something like sort of the kinds of branching involved in, say, a data type which is captured as, say, an abstract trait, a sealed abstract trait with multiple case class subtypes. So that these kinds of you could think of combinations of those sorts of things as being, in some sort of very general sense, sort of shapes of data. And the idea is to be able to write programs which are polymorphic in those shapes, or write programs independently of any specific shape that some particular thing might have. There's a whole stack of applications for this, most of which are, with slightly less highfalutin language, are extremely familiar. Any kind of generic tree transformation, or any kind of generic sort of fold over a tree that you might want to write. Any huge amounts of sort of things like XML or JSON processing craft could be characterized as some form of generic programming.
So maybe I can give what I consider a couple of simple examples that might help people get a handle on it. One of them is if you've got any kind of collection, regardless of what's in there, you can usually find the length or take the second element, as long as it's got two elements out of it. And you don't really care what's in there. What you're interested in is getting that element, that second element out, for example, each time, or something like that. So is that kind of one of the things you're talking about, maybe?
That's a fairly simple example.
Yeah.
Maybe actually not. I think there are more compelling examples than that. So
yeah, another one I was going to say was like monoids, like a fold with a monoid type class or something like that, where you accumulate as you go.
That is a compelling example. It's a good one, but I think there are simpler and more compelling examples.
Okay,
so,
go for it.
Some of the simpler, more compelling ones are things like just serializing stuff. A structure built from case classes out to JSON or XML, or going back in the opposite direction and deserializing a bunch of XML or JSON to a case class hierarchy. So you can think of the serialization side of that equation as being a fold over a somewhat complex data structure. I mean, it's very natural to think of it in terms of a fold. The interesting thing is, can you capture the mechanics of that fold in a way which is both type safe and fully generic? I mean, the usual way people will approach that kind of problem is either by writing not type safe traversals. So, in other words, by effectively erasing types to mapping everything to strings and folding over stuff like that. That's one approach to do it. Another approach would be, which is sometimes appropriate, is to write special case custom serializers and deserializers which know specifics of the types. So you can track types through the process, but the downside of doing that is obviously you've had to write some special case non-generic code. So generic programming is about getting the best of both worlds, having the degree of type specificity that you would get from writing manual case-specific code, combined with the generality of having a single library or combinator framework or whatever that's able to do this kind of stuff with arbitrary data types without having to write any additional code. So this is the sort of the stuff we're talking about here, and I guess because this stuff comes from the Haskell world, the option of casting everything to strings is automatically ruled out. That's not even considered as an option. So the problem is...
Oh, come on. Read, compose, show is the answer to all type errors.
Maybe this is true. But I mean, for the case, the scenario that people are prepared to admit to in public is the one where they actually write all the case-specific code, i.e. the boilerplate stuff. And Scrap Your Boilerplate is all about getting rid of that boilerplate code and having fully type-safe but generic reusable code. That's the underlying motivation for this stuff. So anyway, that's the background.
So that use case that you mentioned, is that what the S codec? Is that right? Shapeless codec library.
And that's one example of doing it. Yes, absolutely. I mean, that's using Shapeless's primitives to do binary serialization and deserialization. Exactly so. Yeah, it's a really nice project. I absolutely, it's Michael Pilquist stuff. Anyone who needs generic binary serialization and deserialization, if you check that out, I think it's very, very interesting stuff. It's also very, 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 very heartening to me because I had absolutely no involvement in that project whatsoever. It's been really nice to see people actually taking the primitives and Shapeless and building stuff on top of it. It's completely awesome.
Cool.
Okay, so that's the background, and that's where I started. So the first bits of Shapeless were basically what I think I should probably at some point kind of dig back into the Git archives and dig out that code and have a look at it and see exactly how appalling it probably was. But it was a very, very early iteration of stuff that was there that's continued in the current form of the library. So that was sort of step one. Sort of following on from that, I guess I ended up in the process of doing that, I ended up almost by default generating sort of putting together some sort of simple HList-like structures, and I certainly wasn't the first person to create HLists in Scala. I mean, there are several other implementations around. I'm sure Daniel has 3 or 4 tucked away somewhere.
None anywhere near as cool as Shapeless is. Mine kind of stop at some point, and I'm like, oh, length is hard. Okay, I'm done.
So Jesper Nordenberg had a really quite nice library called Metascala, I think, which it's still out there. I think he's still working on it, which has an HList implementation. There's also a very well-known blog a sort of joint blog by Mark Harra and Runar.
I maintain those now. The SBT HLists. Those are, I maintain those now. Yeah.
Aha! Awesome.
We go all the way to A list, by the way.
So Josh, you're actually making money. You're making money off HLists.
Yeah, you could say that, I guess. We go H-list, K-list, A-list, and the A-list is actually what we're using for our internals. So
maybe you should tell us what a K-list and an A-list are.
You're going to be very picky about the kinds of elements it allows in.
Yeah. Well, actually, I had a question relating to that because Mark Harra described designing H-lists, because there's an H-list in Scala in depth. And then this is, from my experience, also true, but it didn't resonate until Mark explained it. When you design an H-list in Scala, you are optimizing for a particular use case, always, because there's different ways to encode it. So if you were to say, what is the optimization that you've designed for Shapeless, because I feel like Shapeless has had the most amount of any of the H-list implementations, you have put the most amount of work in.
Yep.
So the question is, did you optimize for a specific use case and implement the rest, or do you feel that it's basically solid on all fronts?
That's an interesting question. Right. Well, I think the general focus of Shapeless as a whole, and that includes Shapeless's H-lists, has really, right from the outset, been on doing as much as possible to get the most expressive power that's available. If I've ever been faced with a choice of performance, expressive power, pick one, I have picked expressive power. As it turns out, I actually don't think that the way that H-lists perform in typical scenarios is particularly shabby anyway. But that's never been the primary motivation for what's at work. The truth of the matter is that the H-lists themselves, although they you started this show off by saying, is Shapeless just H-lists? Shapeless really isn't H-lists at all. I mean, H-lists are just one, if you like, low-level implementation detail of this bigger generic programming picture. I don't know if maybe. Do you want to throw in some more questions, or I could sort of continue with the route from scrap your boilerplate via.
I think we should. I think we should. Yeah. Sorry, Josh. What did you say?
Oh, I said yeah. You should continue with more about generic programming.
Oh yeah.
Enlighten us. Yeah.
Cool. Awesome. So after the scrap your boilerplate stuff, I ended up sort of creating some initial sort of HList type stuff to start with, and I kind of got a little bit sidetracked with that. So it certainly looked very interesting. I could see that there were some other HList implementations around. There was this very, very specific special case of generic programming which seemed to be handled very, very nicely by HList, and that's the sort of the problem of the fixed arities that we have in Scala. So we have tuples which are we've got a fixed bounded set of sizes. Our function types are a fixed set of arities. And there really aren't any particularly nice ways of abstracting over those kinds of things. I mean, it's really very, very awkward indeed. There is no way of writing a generic function that will take a tuple of some unspecified size n and a function of the same unspecified size and apply one to the other, which is it can sometimes. I mean, describing it in that kind of abstract kind of way makes it sound like a fairly obscure and esoteric kind of operation, but it actually crops up all over the place that you might want to do this kind of thing. I mean, and the ability. I mean, so I can give a concrete example of that. So suppose you are trying to, I don't know, compose a whole bunch of validations. I mean, you can use Scalaz's applicative builder to do this, but that's even that's not fully general. I mean, it is bound by the same number of fixed arities that are actually supported by boilerplate code in Scalaz. It'd be really nice if we could just, with full generality, say we've got a function from some bunch of types to some result type, some elements of a case class and a resulting case class, and we've got a bunch of things that are going to produce options of those values or validations of those values, and we're going to lift this function into the option or into the validation in a fully generic way, so that we can take whatever case class constructor we've got. We can lift that into the appropriate monad and get a sensible result out without having to write masses and masses of boilerplate code. And this is something that HLists will actually allow you to do relatively straightforwardly. There's now a very nice implementation, for instance, of something related of say sequence in Shapeless contrib. Which is fully generic and very, very useful, I think.
So did I catch that you're going to make a new validation library that's better?
No, absolutely not.
No,
absolutely no need to do it. I mean, this is what I mean. Okay, well, I mean, this is another. We can maybe talk about the type level projects a little bit later on, but no, I absolutely do not want to reinvent any of Scala's.
But related. You can take validations out of Scala's and functions that do validations and use them more generically with Shapeless?
Well, you can use Shapeless in conjunction with Scala's to compose parts of Scala's in ways which are tedious to do without.
Yeah. I mean, the most gunky aspect of code, in my experience, is when you're mixing validation and any other type constructor with validation.
Well, this is why we have monad transformers.
Yeah, I would not say that is an elegant solution to the problem.
No, it's not great, but I mean it does work.
Right.
It at least collapses some things together.
So there's a quick question about what's a K-list and what's an A-list. I'm just going to answer real quick.
Oh,
because
questions.
it's related. A K-list is essentially, so an H-list is you have a list with arbitrary types, and those types can be different, right? A K-list, it's arbitrary types inside of a type constructor. So it'd be arbitrary types inside of a future, arbitrary types inside of validation, right, or inside of a list. So you can have multiple lists of other types, and many of these. An A list is multiple type constructors. It's one level removed. It's the next level of abstraction. So as soon as you have two type constructors, so you have a future validation of something, and you want to abstract over the somethings, and you don't care that it's in a future validation or a validation of something else, that's when you start to use A list. So I don't want to distract from Shapeless. I just wanted to get that out of the way because we mentioned it and people are.
So really quick caveat on that. It is worth noting that both K-list and A-list are fundamentally unsound in Scala because of the way that variance is handled. So you have to be super careful with them.
But it works.
It does work. Just don't throw anything that's covariant in there.
Why would you use variance?
So the problem is not that. So the problem is that, like, if you have a type constructor, like if you say you have a polymorphic type constructor that has no variance annotation, so no pluses or minuses or anything like that, you just say like f bracket underscore bracket, right? Scala does not interpret that to mean this is a type constructor that is invariant, as it would be if you had like class f, of A with no plus or minus. It interprets it to mean this f is a type constructor that could be invariant, but could be covariant or could be contravariant, and it will allow you to put anything in there. And through this, you can, it's basically an unchecked variance loophole, and you can get, if you stick a covariant type constructor in there, but you're using it in a invariant or contravariant way, you will just completely screw yourself. It's really dodgy, so you have to be very careful when you're doing things with K-lists and A-lists.
So I think you're probably right as far as A-list. So for what it's worth, Shapeless doesn't have an A-list. So it basically, Shapeless's H-lists are of all its elements are of kind star. Shapeless doesn't need, on the other hand, a K-list at all, because a K-list is an H-list with a constraint on the types of its elements. And the constraint is all of the elements share a common outer type constructor. So H-list has got a bunch of, it's kind of interesting. I mean, they currently have rather cumbersome names. I mean, I've come to think about these kinds of things in a slightly different way in the process of putting them together. But essentially, a bunch of little proofs or little lemmas. They're sort of implicit witnesses to the fact that that a given H-list, all of its elements share a common outer type constructor. So that's something which, and I guess actually this backs up to maybe your question about what Shapeless is optimized for. I suspect that the K-lists that you're using in SBT and elsewhere maybe are possibly slightly. Hello?
Yeah.
Still here.
Can everyone hear me?
Yeah.
The A-lists in SBT are optimized for transformations, natural transformations. That's specifically all it's optimized for. Can you hear me?
Can you hear me?
Okay. Good.
Yes.
I can hear all of you.
Okay, cool. Sorry. There's something.
That's all right.
Yeah, right. So no, Josh, you're absolutely right. I mean, the thing is, there is a different approach to this kind of stuff, which means that I mean, the H-lists in Shapeless are perfectly capable of both representing what are being represented by K-lists and also handling natural transformations. One of the earliest breakthroughs, well, I describe it as a breakthrough. It's a breakthrough for me, at any rate, was working out how you could actually do effectively perform a map over an H-list.
Yeah.
So,
well, and to do so with type inference, I guess, is what I mentioned with optimization, because you want the type inference to figure out as much as possible. So ours are optimized where when we pass these setting transformation functions on things, it can rip through the whole settings, understanding the underlying types and everything.
Yeah, sure. But you don't need a special purpose K-list structure to do that. It can be done with an H-list.
That'd be super handy. Maybe we could work together.
Sure. I mean, it's a very straightforward. I mean, look at map on H-list. Map on H-list and Shapeless is polys. that has a whole infrastructure for very, very straightforwardly applying a natural transformation to an H-list.
Well, actually, there's kind of a caveat there, isn't there? Because now I don't actually know the full details of this, because this is something that Lars told me. But my understanding is that as soon as you start getting into some of the more chained implicit machinery, which Poly does in Shapeless, you run afoul of some of the deconstructive type inference not working anymore. So specifically, Scalawag's unapply. Like you can't go through a shapeless poly and then use Scalawag's unapply to pull the type back apart again.
You can.
You can?
Oh yeah.
Okay. So I don't know the full details of this, but Lars was telling me that this basically made it such that you can't use Shapeless and monad transformers and Scalawag's all in the same project, because it basically, like, the type inference just falls over.
I'd need to see a specific scenario, but I'd be very surprised if that was true.
Cool.
I mean, well, okay, Lars is a smart guy. I mean, if he says that, then there is probably
right. But you're getting this kind of third hand, right? Because Lars said it to me.
But right? I can see absolutely no reason in principle why those things shouldn't all fit together in a single project. I mean, there may be some specific case which there is an issue with. I don't dispute, but I think in general I don't think this is a problem there.
Okay. Well, I'll see if I can get a more specific example for you.
Then send me a gist, and I'll take a look at it. But Josh, really, there is absolutely there. I mean, I actually think that's if I were to say what if I mean I don't want to I don't want to be in any way rude about the stuff that Mark or anyone else did with their H lists, but I think actually Shapeless's unification of H lists and things like K lists is actually one of its main contributions, and the mechanics underlying the Shapeless polymorphic functions and the mechanics of mapping those things across H lists is actually quite a big deal. I think it's kind of quite interesting.
Yeah, I like theoretically I agree that that's possible, and you shouldn't have to have something specific. The only reason it exists, as far as I understand, was to make the type inference and stuff just be magic.
Well, the type I mean, seriously, the type inference in Shapeless here is at least as good as anything that you'll find from that stuff. I mean,
I don't doubt you. What I'm saying, I'm just explaining why ours existed. Again,
I totally understand that. Yeah. The thing is, I discovered a new trick after Mark wrote that stuff.
Ooh. So what's the trick?
What's the trick?
Yeah.
The trick is the representation of natural transformations. The representation of the way I represent natural transformations is as a special case of a polymorphic function value with type-specific cases. So that's the general thing. That's the thing I pulled out of Scrap Your Boilerplate, in effect. So I kind of took that from the Simon Peyton-Jones stuff. Roughly speaking, his idea was that you capture when you're chasing a function, either to perform a fold or to perform a transformation, a map or a fold across a heterogeneous data structure, whatever shape it is. What you need is a function which kind of varies at the types of the individual elements in the structure. And SBJ's observation was that, well, actually, this is something we do all the time in Haskell using type classes.
Yeah, so I was going to say type classes would fit that.
So what he did was model the idea of a fold over a general data structure or a map over a general data structure as effectively a case class and a family of instances corresponding to the elements in the data type. And that's kind of exactly what I've done with Shapeless's polys. And effectively, a shapeless poly is a little locally defined type class which has cases for a finite set of types. Well, no, actually not a finite set of types. Well, for a finite set of, if you like, type patterns, where those patterns can include quantifiers, type variables. In effect, and it's those things which, and the key thing is that they can be represented as values, the kind of values that you could pass to a higher order function like a map or a fold, which do all the heavy lifting. natural transformations drop out of this as being a very, very simple special case of that general structure. They are just polymorphic functions which have a single case which has one type variable in it, and that allows you to go from an f of t to a g of t very straightforwardly.
I don't know if we describe natural transformations, but you have a great example in your docs of there's a natural transformation takes a higher kind of type and transforms to another one, essentially. So I can go from, in the example in the docs, if you go to Shapeless and read it, from set to option, you can make a transformation that like grabs the first element if it exists and turns it into an option. Or actually, list would be better. So the head method that you call on list could actually work against any collection at all, and you just make this transformation that says, given a collection, give me an option, and you don't care what the type is. Like we don't care that it's a list of T or something. So this is, natural transformations are things that encode directly in OO with, if you have a type parameter on a class, any method is kind of a natural transformation when you lift it out, but you can't encode that directly in Scala. You actually have to do some trickery to make that work, and that's Shapeless has it, which is beautiful.
Yeah, well, I mean, it's that mechanism is the thing which allows Shapeless's H lists to completely subsume the K lists that you see elsewhere. So, I think it's well, it's kind of annoying. I have a notoriously unfinished series of 3 articles on my woefully neglected blog on polymorphic functions in Shapeless, parts 1 to 3. Part 3 which is the part which would describe all of this stuff in enormous and incredibly ponderous detail, is yet to be written. It's turning into some kind of Duke Nukem Forever kind of scenario. Well, it will probably never show up, and when it does, it will be very, very disappointing.
I'm looking forward to it. I'll sign up for the beta.
Okay, so we're still on Shapeless. So still on H lists. I kind of want to sort of move past this a bit because although they're an important part of it, and I think working. So I ended up in a situation where I was actually, after I got map implemented nicely, and Daniel mentioned doing length. Length was it's in retrospect it's easy, but actually coming up with it in the first place it was not easy and not obvious to work out how this stuff was going to work in Scala. But there was kind of a sort of a hump that after I got over it, everything else sort of pretty much dropped into place. And I think the biggie was map. Map is a bit more complicated, more complicated to do than things like length and reverse. Which, I mean, neither of those are particularly easy if you've not seen how they're done in advance. But map was the tricky one, and that needed this extra bit of mechanics to get it to work. After I got that, I ended up spending a little while sort of, well, I can actually effectively provide almost all of the kinds of things that we think are sort of collection-like operations, and just apply them to H lists and tuples and this kind of stuff. Take head and tail, take reverse a tuple, reverse an H list, map over an H list, map over a tuple, or generalize over the arities of functions and this kind of stuff. And I think because I was probably doing talking more about Shapeless while I was doing that kind of stuff. I think people quite understandably think that's what Shapeless was about. But ultimately that was really just kind of an underlying implementation detail of the real origin of what Shapeless was about, which was the sort of the generic programming thing. And although it is very important, it's a key bit of the implementation infrastructure. I mean, it's only a part of it, because H lists really only represent sort of, if you like, one side of the data type picture. They represent things which we typically call product types. So they represent things which are, if you like, a concatenation of a series of values. So to have a value of a particular tuple, you've got to have one of each of the elements of that tuple. To have a value of a particular case class, you need to have a value of each of the elements of that case class. And the way that this is typically described as being it's a product in sort of a mathematical sense of the types of the underlying elements.
Yeah.
There is actually another very, very important part of that picture, which is that typically interesting data types won't just sort of add elements; they'll also add variants. I mean, in an OR world, we think in terms of sort of subtypes of some abstract type. In a sort of functional, sort of ADT type world, we think of abstract. We think of algebraic data types which have a number of distinct constructors. This model maps very nicely onto the idea of an abstract trait, a sealed abstract trait with a number of case class subtypes. So when you're thinking of data types in those terms, you're not thinking of having one of everything, one of every element. You're thinking of having one out of n elements. So you're thinking not in terms of this and that and the other. You're thinking of this or that or the other. And these in the literature get characterized as sum types, SUM types. So sum versus product types. And you know we have these in Scala. They're either in much the same way that we have product types in Scala with tuples. So one of the things that's a slightly more recent addition to Shapeless is an almost exact. It's not quite as fully fleshed out, I suppose, as Ageless, but an equivalent of the kind of data structure plus set of operators for sum types that we have for products. So again, you know, they're called co-products. So you will find those in Shapeless under the heading of co-products. So co-products have a lot of very similar algebraic properties to products. Amongst other things, you can map over a co-product, which is kind of interesting. If you've got a function which so a polymorphic function which can be applied to an A and a B and a C, so it's the kind of thing you could map over a tuple of an A and a B and a C because you could transform each of the individual elements. If you also had an A or a B or a C, you could map that same function over it, so long as you were able to sort of select the right fork to take. So this is so if you combine these two things, if you combine the idea of having a sum of products as a general representation of a family of case classes, and you also have the ability to traverse across both the sum part and the product part, hopefully you're beginning to get an inkling of the fact that you could maybe perform some very, very general operations on actually really quite real, complex, and useful data structures. I mean, you know, I have my seal family of case classes, the kind of thing we use all the time to represent, you know, to model, you know, documents or protocols or you know, domain entities and this kind of stuff. And the idea of needing to be able to sort of do some kind of general fold or transformation of these kinds of things is incredibly common. And you know, the first outing I had with some of the co-product stuff as well as the product stuff was at FlatMap Oslo last year, and it was kind of a sort of completely silly question in a way, but I just asked for a show of hands for, you know, how many people have ever, how many people in the audience have spent, you know, a significant chunk of their time writing boilerplate code for traversing nested data structures and you know, computing some value from them or transforming them into some other form. And basically every single hand goes up. Everybody writes that kind of boilerplate code all the time. All the time. It's a significant chunk of what people do. Having general purpose mechanisms that can eliminate that kind of boilerplate code is I think kind of a useful thing to have.
Yeah, I mean, I think that, so, I mean, Miles would know this because he worked on the code base, but at Precog we had, like, we were working a lot with trees and graphs because, language, and one of the most common things that we had to do was basically just traverse the tree and like pull out some values in there, or like transform one node into like some other type of node, but leave the others intact. And there were so many types of nodes and so many different cases to handle that in the average case were just like pass-throughs. And we ended up developing some utilities that were special cased on our trees just to be able to do that in kind of a way that preserves sanity. My understanding, and correct me if I'm wrong, Miles, is that Shapeless gives us those sorts of utilities and more for arbitrary trees, so long as you can provide the transformation.
That's pretty much right, sure. Another place to look for this kind of stuff is inside the Scala compiler. I mean, it is absolutely full of special case folds and transforms. I mean, it's absolutely chock-a-block with it. I'm going to pull a random number out of thin air, and I'm going to say at least a third of the code in the Scala compiler code base is basically those kinds of boilerplate. Possibly more than 30% actually is that kind of boilerplate fold and transform stuff. Of course, there are trade-offs. I mean, the trade-off is the one I mentioned before, which is expressiveness versus performance, maybe. By doing something in a very, very general kind of way, particularly in Scala, which is a language which sort of enables this but doesn't necessarily make it the most straightforward or performant thing to do, the cost you pay for generality is often one in performance. I think a Scala compiler that was reworked in terms of generic programming
don't make it any slower, man.
It would be a lot slow. It will be a lot smaller, but it might also be a lot slower.
I would be.
Isn't the hope that this hypothetical alternative compiler would be incredibly long to compile itself, right? It would take forever, but it ought to run fast, right?
Yeah, I was gonna say, I was gonna make that same point because
all the cell time. One would hope.
Yeah, I mean, how much of the boxing and indirection is actually left over at runtime when you're doing these sorts of things with polys? Like how much of that actually bleeds through, and how much of it is just incredible amounts of exponential search at compile time?
It's interesting. I mean, the stuff that bleeds through to runtime is not boxing. It's not boxing per se. I mean, the issue is that whenever you need to produce a case of a poly to apply to a value, you're effectively having to summon an implicit value. There is a compile time cost to doing that, but obviously there is the runtime cost of that implicit value, which is effectively a function value for a specific argument type. That's got to be got from somewhere. In practice at the moment, that probably means a trivial object creation is involved. So
that's probably like an almost zero performance cost then, especially on Java 8, where you're talking about a more flexible heap and frame elimination.
It's not terrible, but it's not zero.
Yeah, that's something you really need to profile to actually know.
Oh, absolutely. I that's work I haven't done. All I know is I know people are using this stuff, and for their particular cases, it's working for them.
Can I tack a question on this point, because it seems like a natural place for it to go? I'm curious about just stuff as simple as H-lists in there. Do you know anybody that's hit the limits of what you can do? Can you have a 1,000,000 element H-list, for example? Has anyone hit that? Somebody must have done this, and they've hit some explosion point in the compiler where things are
how about 23? Not even 1,000,000, right?
Dick, you've answered your own question. I think they did it. It exploded, and so we've never heard.
Yeah, they were muscle in action.
There was a Scala bug report where somebody was like, I tried to make, I think it was an XML thing where it was like a case class, I don't know, some sort of a case class XML to case class conversion thing where they auto-generated code that needed 99 arguments to the case class constructor. And of course, it didn't work. And then we removed the restriction on case class constructor limits, and now hopefully that 99 case class constructor is happy.
Yeah, because that's exactly the sort of thing we want to encourage.
Auto-generate that. It's good.
Yeah.
So we had a question from the audience that I threw up, which was, and I think it's half answered. Miles, when you say performance penalty, is that compile time, runtime, or both? That's from Dale. I'm not even gonna try to pronounce it.
That was basically my point too, in joke form.
It really depends what you're doing. I mean, I think that probably some of the most sort of compile time performance intensive stuff that I tend to do is actually compiling Shapeless's own tests. Because I mean, you know, I have to test this stuff, and for the most part, the test is actually, does this stuff compile or not, or does it compile in the right way? The actual values I get out the end, you know, they're the least exciting, the least exciting part of the process. So it means I have a whole bunch of tests for various bits of Shapeless, and it takes longer to compile, significantly longer to compile the test than it takes to compile the rest of Shapeless. But you know, I think that's an extreme example. You know, I'm exercising every single part of Shapeless for a wide variety of different kind of sized a wide variety of different size scenarios. So that's going to be a bad case, but it's not dreadful. You know, I've worked with code bases that have much higher compile times and test run times than these kinds of
things. I'm sure we all have, yeah.
Oh, sorry.
I think if you're working with H-list kind of structures which have less than 20 elements to a case class, and less than 20 branches to a sort of a family of case classes, and unless your entire code base is made up of examples like this, you're probably not going to see a problem.
Yeah, no, I back that up.
You see a problem, it's going to be less. It's not going to be.
I definitely go along with that. We use H-lists, and that's not high. It's not even on my radar of things that are slowing us down. There's plenty of other meat to go down first.
With the way
there are things
with the way incremental compilation works now, I think the biggest thing that will kill you is the cake pattern, more so than like implicit search will impact you, but ideally you're not recompiling those files all the time, right?
So another thing to bear in mind is that the cost is very, very localized. So you're seeing the cost at a call site, at the point at which implicit resolution has to be done. So once if a given call site is unaffected by changes elsewhere in your system, you won't see any further costs from recompilation. That should be just fine.
Right. So for people who want to optimize, I think the best way to optimize Scala compiler performance is to decouple dependencies, rather than to hyper-focus on, like, this particular line takes a long time to compile. Focus more on the architecture of your system and make sure that when I compile this, it's relatively isolated to change from other pieces of the system.
Well, I think there's two sides to that, because, like, you can use the cake pattern, right? And you can even have modules that have fairly extensive dependency hierarchies. And while there's certainly stuff that will be crazy because, everything in the universe depends on it, like, that's kind of legitimate craziness, right? Because SBT isn't doing anything, or the incremental compiler isn't doing anything strange there. In my experience, as long as you're not like using the cake pattern awfully, like everything depends on everything just because it's convenient, because you can, and cyclic dependencies.
Wait, it's possible not to do the cake pattern awfully?
So as long as you're not doing things like that, I have actually had more problems with the compiler taking a long time on things like mapping with a partial function and trying to infer the type, and doing implicit search in a scope that has a lot of implicits.
Yeah,
like, those sorts of things kill me a lot more than the cake pattern does. Even though the cake pattern does sort of defeat incremental compilation, it's doing it intrinsically. It's not sort of an artificial thing. So when, like, I think it's important to draw the distinction, because when you talk about like the cake pattern defeats the incremental compiler, people hear that and then they're like, oh, whenever the compiler sees, trait X with this, with that, it just turns off incremental compilation, and that's completely not the case.
No, and I mean, there's work being done to improve that. That's a solvable problem.
Yeah, and even the state it's in right now, I'm not dissatisfied with it. I think the compiler actually does a very good job, and it's totally usable.
Well, in any case, when it
Shall I
comes
drag
to
us back
performance,
around?
always measure your performance.
Yeah.
Let's drag it back to Shapeless, because as fascinating as I find this, I think that this is something we can talk about anon.
Later. What I'd like to do, if we can, we have a bunch of questions lined up here. We've been talking for an hour. Should we start answering some user questions?
I want to throw one more in, just a softball knob for please for Miles, which is the other thing I'm aware of but have not yet used in Shapeless is lenses, and I wondered if you can just extol a little bit on what lenses are and what they might be useful for.
Okay. I'm gonna sneak in one other thing first. I'll try and do. So the thing that comes first is so I described how we got, on the one hand, these families of case classes, and on the other hand we got H lists and sums of products.
I thought you were going to get there from here, which is why I sort of threw this.
One thing I didn't mention is how you get to one from the other and back again. And that was something that arrived. It arrived in fairly early on. I mean, it was certainly there in sort of Shapeless 1.2 ish, and that's it was called ISO then. Currently, it's called generic, and basically it's one of a very small number of very focused macros that exist in the current Shapeless code base. And what they do is they provide an automatic mechanism for taking you from a value of a case class type to the corresponding H-list type that you would expect to get by, if you like, unpacking the elements of the case class. Or in the case of an abstract trait, sealed abstract trait, it will get you from a value of that type to a value of the co-product type, which is the value you started with, but sort of injected into this sort of nested either-like structure, so that we got some kind of an encoding of which branch of the sum you went down. So that's what generic does. So the fact that this is it's a Scala macro. It's the additional bit of magic we get here is that effectively you've got this transformation from sealed families of case classes to a generic representation, which you can then operate on using the various bits in the Shapeless toolkit. That's a very important part of the picture, because that completely eliminates a huge chunk of the boilerplate code that people typically have to write for this kind of stuff. So there's another thing which sort of arrived very recently, and that's labeled generic. So labeled generic is just like generic, only it adds labels. And labels are one of two things. In the case of a case class, the labels are, if you like, the field names of the elements of a case class. And in the case of a that's a product type. In the case of a sum type, the labels are effectively the names of the types. So we've got a trait which is extended by case class A, B, and C. So the labels here are A, B, and C. So they're telling you which branch you go down from your abstract type to the concrete case class. So what we end up with is a labeled sum of products representation of a value. So a labeled product basically looks like a record. It's kind of an H list with a sort of key value pairs.
Yeah.
And we've got infrastructure in Shapeless for indexing into that record-like structure using a representation of the key to get the value out. This is all completely type safe. It actually turns out that the keys themselves are just encoded in the types of the values. There's no. I'm quite pleased with this. I mean, there is absolutely no in-heap representation of the keys in these maps. Oh. The encoding of a Shapeless record is exactly the same in terms of memory footprint as the encoding of the H list of its elements. It's kind of a cool trick. I'm quite pleased with it.
Yeah, that's awesome. And do you use that for the zippers as well?
So the generic stuff is used for the zippers. At the moment, the generic zipper, that's just encoded with sort of doing left, right, up and down kind of stuff through the structure. It's on my to-do list to do something with the labels.
Like skip the label or something, yeah.
Yeah, sure. At the moment, the zippers are only using generic, not labeled generic.
Oh, okay. Okay.
So okay, there's a couple of things that drop out of this. I mean, I really want to. I mean, one of the things I really want to try and do is promote generic and labeled generic as being, if you like, the key primitives for doing sort of generic programming and sort of building more interesting and more sort of high level things on top of it. Building some kind of serialization or deserialization framework on top of something which both represents the sort of the values and also the names of the values. I think that's kind of it's kind of obvious how that sort of works.
I think this label generic, and it's so new in Shapeless 2.0. I don't think that the community has it's exciting that this is getting off the ground.
Sure. I mean, it really is very new. I mean, it's really only arrived in the last couple of months, maybe. Not much. It's not much. Basically, it came just before I made the final release of Shapeless 2. So it is very, very recent. Okay, so that's label generic. So lenses you were asking me about. Basically, they are built entirely. The current iteration of Shapeless lenses are built entirely on top of label generic. I'm absolutely. I mean, I'm extremely pleased to see that there are no new macros at all needed to implement the current form of lenses in Shapeless. If you look, I mean, basically the Shapeless lenses are written in, I think, close to optimal Scala syntax. I don't think there's much more you could do to write the sort of the expressions for constructing lenses and prism-like structures as well, any more succinctly than they are. Typically, you would. So it uses Scala select dynamic to actually allow you to use to effectively pick out names and use that as a mechanism for constructing the lens. But it does so in a completely type-safe way. I'm not the first person to do that, but the existing things that do it in a type-safe way do it by implementing select dynamic with a macro. So the macro obviously is then free to kind of inspect the target types and expect the value that's handed to the select dynamic call and make things line up. That's not a bad way of doing things, but the minute you're doing anything with a macro, you've stopped programming in Scala and you've started programming in Scala C, which is fine if you have to. If you absolutely have to, it's fine. But I think ideally we probably want to carry on programming in Scala for as long as we possibly can. Using label generic as a primitive, again combined with sort of things like the product and co-product sort of selection operations that we've already got built on top of Shapeless records and labeled unions, which are basically the labeled equivalent of a sum type. You can do everything. You do not need any additional macro magic to get this kind of stuff done. I'm quite pleased with it. The new lenses they're in Shapeless 2.1 snapshot. They're not part of a release yet, but I think they're interesting enough that I'm going to try and get a Shapeless 2.1 release out as soon as possible. There's one complicating issue here, which is there is another really very interesting Scala lens project which is in motion at the moment. It's called Monocle. Monocle is It's a great name, and it has a really nicely put together logo. I encourage everyone to take a really close look at it. It's good stuff. It's an attempt to translate Kmet's Haskell lens library to Scala, and well played.
Sorry, carry on.
Yes. Where was I? You've completely.
I'm sorry, Miles.
Yeah. So I'm talking to the people who are working on that project. And basically, I want to see shapeless lenses go in the direction of Kmet's lenses. I think to do that properly depends really on having a much closer relationship with bits of Scala Z than I currently have. Basically, Shapeless intentionally has almost no dependencies at all, for a variety of reasons. I mean, some of them historical. I mean, certainly in the early days, I wanted to be basically to be able to say I have complete freedom to do whatever the hell I want, including up to and including forking Scala C to make it do things the way that I wanted it to do, and that was pretty much. Made it essential that I avoided having any dependencies. So I've avoided having any Scala Z dependencies. On the other hand, I don't want to reinvent Scala Z. I think it's a fine library. I think it should be part of everybody's Scala toolkit. So what's happened is that under the umbrella of the type level project, there have been a number of, if you like, contrib projects, which basically allow various components of libraries to be spun out as separate modules, so that they can grow dependencies that they couldn't otherwise have directly. So there's a Scala Z contrib, there's a Shapeless contrib. The Shapeless contrib library is able to have dependencies both on Scala Z and on Shapeless. So I think probably what's going to happen once I've kind of worked through once I've kind of scratched my own Shapeless lens itch, is that I'm going to spin out Shapeless Lens as a separate project which can have a Scala Z dependency, and I'm going to hopefully work with the Monocle people to try and come up with, if you like, the definitive Scala Z, definitive Scala lens library, which gives us the best of all the worlds we can possibly hope for.
Cool. Is it all right if we go through the user questions now?
Yeah, please do.
Cool.
Sure.
All right, so there's actually votes. So we're going to start with questions that have more than a vote. Yeah. So the first one is what happened to your unboxed tag types? I don't see it in the Shapeless docs, for example, int at you.
They've moved around. I mean, if you look in if you read the documentation, you'll find that there's a migration guide from Shapeless 1.2.4 to Shapeless 2, which will tell you that tag types and new type have moved, and they are now found under a tag and new type import. So if you can find that on the migration guide, and that'll tell you where they are. It's kind of interesting whether or not. I mean, tag types are useful. I mean, I think they are, I think, definitely kind of pretty close to the edge in terms of legality. As far as, I mean, they are definitely.
I believe the word you're looking for is a really neat hack.
Sorry.
I think the word you're looking for is a really neat hack.
A really neat hack, which has sort of some justification theoretically, but you could equally go the other way and say it was basically a soundless hole in the Scala type system.
You're punching. I mean, you're using as instance of to make one, right? So automatically you're punching a hole.
Yeah, but I mean the actual.
This is a friendly hole.
It's a tiny hole. It's like a little wormhole.
But these go to 11.
I've used them. I think they're neat. I also, the first time I used them, I thought, I cannot believe you can do that. That is such a neat hack.
It's okay. After we punch the hole, we cover it over with duct tape, and then we punch it again later. It's fine.
So the main use. I'd say the main use for the main legitimate use for these things is effectively to do what you do in Haskell with new type, and it's for guiding type class resolution. So you might have you have multiple monoids for integers, for example. So you might tag int at additive or int at multiplicative to get the corresponding monoid. The way you would do that in Haskell you would have a new type for int to select one of the different one of the other monoid instances. So that's useful.
Cool.
I'm using tags to encode the record labels and disjoint union labels. So that's the way it gets the sort of the zero footprint encoding of the labels. So that's the singleton type of the label is intersected with the type of the element via a tag. So we're using singleton. So a type level encoding of.
That's awesome.
Sorry.
So
it is pretty awesome. It makes for some really exciting looking types, I can tell you.
I can imagine. I can imagine that some of them might not even be expressible in the syntax of Scala.
No, all the types I use are expressible.
Okay, that's good.
Nothing.
I've only ever dealt with one type that wasn't expressible in the syntax. That was fun.
Which type?
Well, technically, so types with free variables are not expressible in the syntax directly, but you can trick them into the syntax.
Yes.
Sure.
Anyway, okay, so let's move on to the next question, which is, what's the Haskell equivalent to Shapeless?
Well, it depends which bit of it you're talking about. The stuff that I'm trying to focus on the most in Shapeless at the moment is the generic programming aspect. So things like generic and label generic. That is GHC generics, and that's that is Andres Lowe and I'm very embarrassed I can't say who the other was. They arrived in GHC 7.4.
We can always put them in the show notes afterwards. So
if you look for GHC generics on the Haskell wiki, you'll find it. And they actually, I think, right. So they arrived in GHC 7.2. So they are a relatively recent addition to Haskell, to GHC specifically. So we're kind of just about keeping up with this kind of stuff, which is nice.
So yeah, so cutting edge, nice. Next is I don't think it's really a question. It's just a statement, but it had a vote. So Dick, you want to hit the compiler stack space limit?
No, I really don't want to hit the compiler stack space limit. That happens way too much. I'd rather not do that.
I'd like to clarify that the stack size limit is actually on the JVM. The compiler just makes it friendly to hit the limit.
The compiler pushes the limit pretty hard, yes.
Except for the like one or two places where it's actually tail recursive, and you can get something that does in fact compile forever.
Yes, I've also had that situation too. Yeah.
There's this thing that you do when you're making a binary compatible library where you want to add an argument to a method, but you can't remove the previous method. So you make a new method that takes that additional argument, and you have the old method delegate to it. And what this naturally does is mean that your stack size of your program just grows and grows and grows and grows as you stay compatible. That is my favorite part of maintaining a library, is watching that stack size get bigger.
You need to break stuff occasionally. That's the answer to that.
Yeah, well, we're working on that. Anyway. All right, so the next question. Miles, is there anything in Shapeless you might say is a little flaky? And I might want to wait before using.
Oh, okay.
Good question.
That is a good question. There is actually one thing that is a bit flaky and will probably may even get removed fairly shortly. So one of the things that I did a bit of work on last year, and I even did a talk about it at Scala Days last year, was again using a macro, a mechanism. So one of the things that's not completely cuts with the grain of Scala syntax is the way that you construct shapeless polys. I mean, we're used to the idea of being able to just write a function literal or an inline function, and you use that as an argument to a higher order function like a map or a fold or whatever. So shapeless polys basically have to be constructed as first-class values with singleton types. I mean, it's not completely true, but to a first approximation, to define a poly, you have to create a Scala object and have at least one definition method definition nested within it. This is a little bit more ceremony than having a sort of an inline lambda. So one of the things I played around with is so there are a number of special cases, interesting special cases. Some of them being natural transformations are among them, where actually it's there's a fairly simple sort of lifting operation that you could do to turn a vanilla function into one of these things. It's not something that you can easily directly express in vanilla Scala, and I did some experimentation with a Scala macro that would lift either a method on some other object or class, or a function, an inline function value into a shapeless poly. So it automatically create that object wrapping around the method call or the function, the inline function definition. Kind of worked a bit. There was a whole bunch of bugs in Scala compiler and the macro implementation at the time, and that was sort of, I think, pre-Scala 2.10, so it's sort of 2.10 milestones. I'm pretty sure I was hitting some similar bugs to ones that Heather and Eugene were running into with the spores stuff as well. And I believe, actually, I think I vaguely remember having a chat with them and also with Jason Zhao. And I think there were some bugs that were fixed actually during Scala days to help Heather and with their stuff. It's quite possible that some of those problems are actually easier to solve now. It's also possible that some of the new SAN stuff, which is coming in 2.12, is sort of vaguely related to this as well. The truth is, although there is code there which sort of pretends that it does this lifting, and in some special cases it sort of does it. It basically doesn't work properly, and I should probably have taken it out already. But I mean, I do hope to be able to sort of at some point come back to this and make sort of, if you like, inline polymorphic function definitions easier to do. So you should definitely regard that as being a placeholder for something that will be better at some point. And it's definitely flaky. Flaky though is only flaky in the sense of compile time flaky. It's stuff that will just not compile the way that you want it to do. I don't think there's anything actually runtime flaky anywhere in Shapeless, because things really only ever go wrong at compile time. I mean, everything else is largely at runtime. Everything is pretty straightforward. And it would be quite surprising.
At runtime, Shapeless is fairly trivial. It's all just compile time. Nothing else is interesting.
Well, the compile time is the runtime.
Exactly.
Yeah. You're trying to take something else that happens at runtime and do enough work at compile time that it is easy. Yeah. Right? Anyway, so the next question is, what is the either-like structure you mentioned we get from a sealed trait? So is it that... just so I understand, like, in Shapeless, I can take, say, a sealed trait, and I can grab a co-product of the sealed trait where all of the possible subclasses are elements of the co-product?
I mean, there are some restrictions here. I mean, the only data types that I attempt to support and have any plans to attempt to support are things that map fairly directly onto, say, Haskell-style algebraic data types. So this is a sealed trait which has a number of case
classes, yeah.
Specifically case class concrete implementation.
Yeah.
So in that case, the co-product type, the either-like type, is if you have a value of one of those concrete classes, then you've chosen a branch to go down from the abstract type to the concrete type, a value of any one of those concrete classes is an instance of, suppose we've got some trait, I don't know, animal, and we've got concrete case classes, cat, dog, cow. So a representation of animal is as either as cat or dog or cow, and if I have a particular animal, any of those animals can be injected into that sum type. There will be some in the same way that it can be injected via subclassing, via the subtype relation into excuse me into the animal supertype. So really, what's going on in a way is that the co-product type here is actually reifying the concrete subtype that has been selected by picking some particular concrete implementation.
So and is co-product the either-like structure?
Yes, that's right.
Okay.
It's either with more, because you can have arbitrary length eithers, basically, right?
Well, I mean, one way of so there is a sort of a slightly trivializing way of characterizing both H-lists and co-products. I mean, you could say that an H-list is just a nested pairs all the way down. I mean, that really is all it is. It is basically that, and a co-product is really just a nested either all the way down. The key thing that makes it slightly more interesting than that sounds is the fact that you can also define operations over those things.
Plus, you've abstracted away the whole nesting thing, which would look ugly. I mean, let's not overlook that as a benefit.
What do you mean? Yeah. I love brackets in my code, as many of them as possible. It's
lots
like
and lots of square brackets.
It's like type Lisp, really. Like your types
Lisp,
are just a
Lisp with square brackets.
Yeah.
With every element surrounded by square brackets.
Yeah, and
it's how the notation should have been in Scala. If we had Lisp literals,
type definition is 26 closing square brackets.
Yeah.
Yeah.
Exactly. It's Lisp at the type level.
Well, this is why I'm involved with language design, working on SBT. Oh, anyway.
Great. This puts all of our minds at ease, Josh. The next syntax for SBT is just going to be like it's a whole bunch of square brackets opening and closing, and like some commas somewhere.
Well, so we're
underscores too.
We're gonna take the ever popular JSON spec and just alter it to be brackets and more listed. And that's the new DSL that's coming out. So just wait, it's coming. All right.
Nice.
Anyway, the last thing is the last question. I think you already answered this through describing, but Miles, you mentioned generic programming. Don't you want to describe what it is, assuming you didn't already? And I think you went through it again, but I think it's a great cap to the whole episode. Is what like another definition of generic programming to end it out.
What, different from the one I gave before?
I was going to say, I do believe we've covered this.
No, what I'm saying is you can say it again, just to recap. Shapeless is about generic programming. It is not about H-lists.
Yes, that's right.
That is absolutely, and I guess I really do want to emphasize that. H-lists, they're important. They're an important part of the route I got to where Shapeless is now. I would really like people to think of Shapeless now these days as being a generic programming library for Scala. That's pretty much what it is, which have H-lists as an implementation detail. Definitely.
Yeah.
I would if I was able to, I would actually rename H-list to product. But sort of historical baggage makes that impossible, and the fact that Scala already has grabbed that name makes it quite difficult to do.
Yeah. So,
excellent.
I'd just like to mention. I'd like to mention a couple of other things quickly. So, so one of the things that we sort of actually Dick mentioned it very briefly. I mean, he was talking about using the sort of generic programming mechanics in Shapeless to derive type class instances. So you were talking about doing monoids for arbitrary cases, things like that. This is absolutely awesome stuff. This is work done by. Or a big chunk of it, at any rate, work done by Lars Hoodball, who's I'm sure everybody knows him, but is the current main Scala Z maintainer. He put together the type class, which is an awesome name, which is basically provides some really nice mechanics for allowing you to automatically derive type class instances for some of the product types. And it's very similar to facilities that are available in recent iterations of GHC. So again, this is pretty good stuff. This is stuff that's very, very valuable. There's some nice examples of doing that kind of thing in again in Shapeless Contrib, where it's possible to sort of depend on more libraries than just JUnit, which is Shapeless's only dependency. There's some very nice examples of using the type class to derive Scala check instances. I mean, if you want to just be able to, you have some sort of families of data types, maybe they're sort of protocol elements or something like that, or bits of JSON or XML encoding or something like that, and you want to just arbitrarily generate bunches of stuff to fire at something. You can automatically derive Scala check generators for these things, and that's a pretty useful thing to have, definitely. So I wanted to mention that. And what else did I want to mention?
Are you going to be at Scala Days? Giving any talks?
I'm going to be at Scala Days. I'm not actually. I haven't actually planned to do a talk about Shapeless at Scala Days for various reasons. I've been sort of vaguely floating the idea of trying to do an ad hoc workshop sort of before or after or something along those lines, but I haven't really got anything planned yet. I personally don't think I'm very good at doing talks. I actually find it much easier to do kind of sort of rambly, free associating kind of workshops where I'm not bound by getting finished in half an hour, and it works better for me if I and all attending if I do.
I've been to the day-long Shapeless workshop, so I can vouch for that format works well.
Cool.
I think it's what I'm best at. But I'm going to be doing a talk at Scala Days. I'm going to be doing it with John Pretty. We're doing a talk on 10 years in Scala.
That sounds awesome. Yeah.
Which I hope will be lots of fun. So I think we have both done 10 years of time as servants of the Scala compiler. I think it's about time to do some kind of a retrospective maybe of that. So we're going to be doing that sort of two-hander talk.
Yeah, awesome. So we'll see you there.
Cool.
I don't think this is working, huh? Hold on. Oh, here we go. That's why.
Or you will miss all that heavenly glory.
To send us out.
MTO.
Thanks, guys, for listening. We have a mailing list called thescalawags@gmail.com. I hope Miles will pay attention in case anyone has Shapeless questions over the next few days or whatever. And thank you so much, Miles, for coming on and talking to us.
I can't hear what you're saying anymore, Josh.
Yeah, you're completely dominated by Bruce Lee, which is perhaps not surprising.
Yeah.
It's as it should be.
Look, be shapeless. So,
I think your words were shapeless.
Yeah, no, come on the mailing list. Hope to hear from you there. Thanks, Miles, for joining. It's been great.
Well, thanks for having me on the show. It's been good.
Yeah, anytime. And we'll see you all for the next episode.